All, Vinod here from Entrance Engineering Academy. Before going into the video, I just want to say a few things about Entrance Engineering Academy. So, EEA is an online GATE preparation portal, and we offer full course for GATE ME and XE. In addition to that, subject courses are also available for ME, XE, CE, and PI. Engineering mathematics course is available for all stream, and in addition to that, we offer online test series for GATE ME and XE also. So this is our website. You can just check out so that you will get to know more about us. And in addition, we have our own Android app and also iOS app, and you can just go through that also to know more about our courses. Okay. And this is our last year, that is GATE 2021 result from XE. And now let us proceed to the video. And this video is taken from online video course of Endurance Engineering Academy. So let us start circular motion. So we discussed about polar coordinates for a general case, right? So now we are going to apply that polar coordinate which is developed by Euler's for circular motion. Okay, this topic is very important not only for engineering mechanics. This is very important for theory of machines also. It's very important for other topics which is related with this particular topic. Okay, so very important but simple only. Just be patient and listen to me, you will understand it. Okay, right. So if there is a particle and if that particle moves in a circle, okay, it's happily moving in a circle. If the particle moves happily in a circle, then according to Euler's, we know that we need to take a center as the pole, and then this is going to be the reference axis, and the particle is happily moving in this manner. So if it moves, then surely theta is going to vary. Obviously, if particle is here, theta will be different. If it is here, theta will be different. If it is here, it will be different. So the particle is moving in the circle, theta, that is angular displacement, will continuously vary. But what about radius? Radius will remain constant everywhere, right? Wherever particle goes, this radius has to remain same only. Okay, everywhere radius will be same only. So radius is not going to vary. So for any circular motion, okay, for a particle moving in a circle, any circular motion, radius will be constant. This is very important point. Since radius is constant, if I differentiate it one more time, okay, what happens? R dash, which is nothing but dr by dt. So constant's differentiation is going to be 0 only. Again, further differentiation, d square r by dt square, that is r double dot, that is also 0 only. So these are the 3 points. Okay, the one is what? Radius will be constant. The first derivative of radius will be 0. Second derivative of radius will be 0 for all the circular motion. Very important point. Note it down properly, highlight it properly. So wherever a particle moves in a circle, radius will be 0, r hat will be 0, r double dot will be 0. Okay, for any circular motion. Okay, not necessary that there should be any other condition. One and only condition is the particle has to move in a circle. So if a particle moves in a circle, as we know that we already derived 3 equations, right? A general equation of polar coordinates. One is position vector, another one is velocity vector, and another one is acceleration vector. Now we identified r is constant. Okay, so if I take position vector, r is constant, then this position vector depends only on theta. That we already know, well and good. Now coming to velocity. Okay, velocity has 2 different components. One is radial velocity and another one is tangential velocity, which we already discussed in the last video. Now radial velocity, okay, is nothing but r dot. But for a circular motion, if a particle moves in a circle, what is going to happen? R dot is going to be 0, because we know that, right? R is constant, so r dot is going to be 0, which implies there won't be any radial velocity. It is very obvious also. Why? Very simple. Radius was remaining constant, so the particle is happily traveling only in circle, right? The particle is not moving away from the origin or towards the origin. Particle is only staying in the origin. It's happily rotating. It's not going away. It's not coming towards. If r dot is positive or if r dot is negative, then the particle may be moving away and the particle may be moving towards the origin. So if r dot is positive, then it indicates that the particle is moving away from the origin. What does it mean? For example, this is the origin, this is the particle. when it is rotating, when the particle is traveling, how it will move? Let us just consider that the path which I am going to draw is the path of the particle. Okay, the particle will be moving like this. What is happening to the radius? What is happening to the radius? Initially this is the radius, then radius is increasing, then increasing, then increasing, then increasing. So keep on, radius was increasing. So when r dot is positive, the particle will be moving away from the origin. Okay, this is the origin. Okay, but when r dot is negative, okay, this suppose this is the origin. When r dot is negative, then particle will be moving towards the origin. Okay, it has to be circular. I'm not drawing it perfectly. It has to be circular. Okay. So how it moves now? It's moving in this direction. Okay, it is moving in this direction. Moving in this direction. Sorry, yeah, in this direction. In this direction. It's moving towards the origin. In this case, it is moving away from the origin. It's moving away from the origin. It's moving away from the origin. It's moving away from the origin. Away from the origin. This is towards the origin. If r dot is negative, this happens. If r dot is positive, this happens. Something like a spiral case of motion. Okay. But if it is a completely circular motion, then r dot is 0, which implies Vr will be 0. If this is the case, then there will be some Vr, radial velocity will be there. If this is the case, also some Vr will be there. If this is the case, then radial velocity will be away, okay, pointing away. If this is the case, radial velocity will be pointing towards. Since r dot is 0, there is no radial velocity. This is the first point. And I hope you would have understood what is meant by radial velocity also. Simply, what is the rate of change of radius? Since radius is not all changing, for circular motion, for any circular motion, radial velocity will be 0. Okay. If radial velocity varies, then based on that, we can say how does the motion happens. Okay. Right. So we got one. Next, Vt, that is tangential r theta dot. And theta dot is what? Theta dot is nothing but how angle change, okay, angular displacement changes with respect to time. So rate of change of angular displacement. If suppose there is a body, okay, if the body moves in this direction, okay, if the body moves in the direction with some velocity, then change of this displacement, okay, change of this displacement with respect to time is velocity. And similarly, if it is rotating, if it is moving in a circular motion, then this angle is also changing, right? That change in angle with respect to time is nothing but angular velocity, which will be represented with omega also. This is angular velocity, okay, change in angle with respect to time. So r into theta dot, I can write it as r into omega also, right? So if it is a circular motion, pure circular motion, not a spiral case of motion, pure circular motion, then radial velocity will be 0, angular tangential velocity will be r into omega. And how does the tangential velocity act? If suppose if the particle is moving in anticlockwise direction, okay, with angular velocity omega, okay, if the particle is rotating or moving in an anticlockwise direction in a circular path, then my tangential velocity will be like this, okay, Vt. Okay. At the same time, let us consider there is a particle, and this particle moving in it's moving in clockwise direction. If it is moving in clockwise direction, then my tangential velocity will be in that direction only. So if the particle is moving in counterclockwise direction, tangential velocity will be like this. If the particle is moving in clockwise direction, my tangential velocity will be like this. Okay, I hope it is clear. Now we got Vr, we got Vt. So what about the next? Acceleration. Coming to acceleration, again we have two components. This is radial acceleration, this is tangential acceleration, right? We already know that r double dot is 0. Okay, so with respect to radial acceleration, r double dot minus r theta dot square. We already know that r double dot is 0 because it's a circular motion, pure circular motion, r double dot is 0. Theta dot is what? Omega, right? Theta dot is nothing but omega, that is angular velocity. So radial acceleration will be equal to minus r omega square. Regarding this term, minus r omega square, there is a name for it, and what does it signifies, all those things you will see a bit later. Okay, and one point to note here, for a pure circular motion, if it is a circular motion, radial velocity is becoming 0, but still radial acceleration was there. How it is, what is that, we will see it later. Okay, right. Now coming to next term, that is tangential. Okay, AT. Okay, tangential, which is 2 times of r dot theta dot plus r into theta double dot. R dot is nothing but what? R dot is nothing but v radial, and theta dot is nothing but omega. So 2 times of Vr omega. This 2 times of Vr omega is nothing but Coriolis's component of acceleration. And this Coriolis's component won't have that much significance in this particular chapter. We have more significance of this in the theory of machines majorly. When there was like this, for example, if this is an hinge and there was a slider, okay, and there was something which is going to rotate, and this slider is going to move, like it's going to move radially that side, and it's going to come radially this side, something like that Whitworth quick return mechanism and all those things. Okay, so this link will be rotating because it is hinged here, right? It is hinged here, so the link will be rotating, and the slider will be moving up and moving down. So radius will also change, theta will also change, and during this case, this Coriolis's component, okay, 2 Vr omega will be significant. So in case of slider and slider crank mechanism, what will happen? This will be rotating. Okay, the link will be rotating, and the slider will be moving up and down. So radius is also changing, angle is also changing. So during that time, we will be having radial velocity also. We will be having that angular velocity also. So during that time, this Coriolis's component of acceleration will be significant. But for a pure circular motion, if it is just rotating, the particle is just rotating in circular motion, obviously r dot is 0. That is, there is no radial component of velocity, so this becomes 0. And what about r theta dot? Omega was there anyways, right? Omega is there. Theta double dot. Okay, so theta double dot is nothing but 2 times differentiation of theta, which is nothing but alpha. Okay, or simply we can write it as d omega by dt, which is equal to alpha. This is nothing but angular acceleration. Okay, so angular velocity means how this angular displacement is changing with respect to time. Angular acceleration means how angular velocity is changing with respect to time. I will just explain the significance, just wait for a moment. So instead of this theta double dot, I can use r and I can use omega. So tangential acceleration is going to be r omega. So finally what we got? So the resultant is, we have rp in velocity vector, no radial velocity, only tangential velocity, that is r omega. Okay, and that will be represented like this. And what about this radial acceleration? If you want to represent that radial acceleration, it has to be represented like this. Okay, it is like this, towards the origin. Why towards the origin? Because of negative signs. Because of that negative sign, it will be towards the origin. What does it signifies? I will just explain. Wait for a moment. So r omega square, that is radial acceleration. And what about this? I'm very sorry. This is r alpha. Okay, theta double dot, right? Theta double dot is r alpha. So that is tangential acceleration. So if omega, that is angular velocity, is acting in this direction, then angular acceleration will also act in the same direction. And angular tangential acceleration will also be in same direction. Okay, so we can write it here, it will be better. Okay, so radial acceleration towards the center, okay, because of the negative sign, and tangential acceleration will be in the same direction as that of velocity. Okay, now what is this overall conclusion which you could get for a circular motion? Simple. For a circular motion, r is equal to 0, r dot is equal to 0, r double dot is equal to 0. Since r dot is 0, Vr is 0, so we have only Vt. Okay, and next is r double dot is 0, so even though we don't have Vr, we will be having Ar. Okay, so Ar will be minus r omega square. And coming to tangential component of velocity, it will be there, and tangential component of acceleration, Coriolis's component won't be there because there is no change in the radial direction. But what is that? R alpha, that is tangential acceleration, that will be there. Okay, now what is this alpha signifying? Okay, what is this alpha signifying? If alpha is positive, okay, if alpha, there are three possibilities. Alpha can be positive, alpha can be negative, alpha can be constant. Okay, alpha can be negative, alpha can be positive. I'm sorry, alpha can be positive, alpha can be negative, alpha can be 0. Okay, alpha can be 0. Okay, what if alpha is positive? Okay, what if alpha positive? That is angular acceleration is positive. So angular acceleration positive in the sense tangential acceleration is going to be positive. So because of alpha being positive, okay, what we are going to get simply omega, okay, which means angular velocity is going to increase. Just consider an example of what is that? Switching on the fan. When you are switching on the fan, what will happen? The particle, that is, you can consider that if this is the fan, you can consider this point to be the particle. Okay, this point to be the particle. So initially, what will happen? Initially, it will be at 0 velocity, and it will start increasing the velocity, right? So the angular velocity will keep on increasing until it reaches some until it reaches some steady state, right? So initially 0 velocity. When I switched on the fan, since acceleration, the angular acceleration is positive, its angular velocity will be keep on increasing. If angular velocity is negative, what does it mean? I'm just switching off the fan, deceleration. Okay, what will happen? The angular velocity will keep on decreasing. Okay, angular velocity omega keep on decreasing. So angular velocity decreasing means obviously tangential velocity omega decreases, so Vt will decrease. So angular velocity increases means Vt is going to increase. You can take an example of switching on the fan. This is switching off the fan. Now coming to alpha is equal to 0, what does that mean? There is no acceleration. You can take the example when the fan is rotating at a steady condition. You switched on the fan and you kept some number also. You used the regulator or you kept it at 3. Okay, let us imagine. So after reaching a steady state, there is not going to be any increase in the speed, or there is not going to be any decrease in the speed of the fan also, which means it's going to rotate at a constant velocity, at an uniform velocity. Okay, uniform tangential velocity. That is the period when alpha is 0, when omega is constant. Okay, when omega will be constant. Okay, fan will be rotating at an angular velocity when at a constant angular velocity when after switching on for maybe after some 1 minute or 2 minutes, once it reaches steady state, it will rotate at a constant angular velocity. There won't be any acceleration. Okay, so 3 condition. Angular acceleration positive means omega will be increasing, tangential velocity will be increasing. Angular velocity negative means omega decreasing, angular velocity decreasing, tangential velocity will be decreasing. Alpha is equal to 0, omega is constant, like the particle will rotate at a constant angular velocity. So now take any circular motion. Okay, so for any circular motion, the final conclusion which I have to give was radius will be always constant, r dot and r double dot will be 0. So since by applying this condition there, we got radial velocity to be 0, there is no change in the radial distance, tangential velocity will be r omega. Okay, so then finally the total velocity will also be equal to tangential velocity, that is going to be equal to r omega. Okay, where omega is the angular velocity rate at which the angle or displacement is changing. And coming to the next, radial acceleration, r double dot won't be there, only r omega square. What is r omega square? I will say it later. And now r alpha, okay, which is the tangential acceleration. And what the tangential acceleration signifying? If alpha is positive, omega will increase, alpha negative, omega will decrease. Alpha, if alpha is not there, if it is 0, then omega will be constant. And now finally the resultant acceleration can be determined by root of ar square plus at square, and this is applicable for any circular motion. Now we will start applying few conditions in the circular motion. Okay, so the representation I did it there. If the particle is rotating in anti-clockwise direction, angular velocity in anti-clockwise direction, acceleration in anti-clockwise direction, so tangential velocity will be like this, tangential acceleration will also be like this, and the radial acceleration will be pointing towards the origin because of negative sign. So now we will start applying few assumption in our circular motion problem. Okay, the first assumption which I am going to include was constant angular acceleration, which is alpha is equal to constant. I hope you could recollect something which we discussed earlier. What is that? We got these two formulas for the rectilinear motion v is equal to dv by dt, and a is equal to v is equal to ds by dt, a is equal to dv by dt. And from this formula, we assumed that acceleration is constant. Okay, a body which is moving in a normal linear motion where the acceleration is constant, and by using acceleration constant, we got these three formulas. I hope you're able to recollect it. Okay, and now angular acceleration being constant, what does it mean? When the body is rotating now, okay, when the particle is rotating now, it is rotating with constant angular acceleration. Okay, so that is something which we are going to discuss. There linear acceleration was constant. Here for circular motion we are assuming angular acceleration to be constant. Okay, so one thing, if it is a circular motion, whatever may be the circular motion, any circular motion, these conditions are true, right? There is radius will be constant, first derivative will be 0, and second derivative of the radius will also be 0. Because of this, radial velocity is becoming 0. Tangential velocity we got r omega, where omega is the angular velocity, and ar is that is radial acceleration is minus r omega square. And what is this? What it signifies? We will see it later. And at tangential acceleration is r alpha. So now because of this condition, alpha is equal to constant, that is angular acceleration is constant. If I make alpha constant here, what will happen? If I make alpha constant here, at will also be constant. That is tangential acceleration is also constant. Why? Because already r is constant, right? Already r is constant. Alpha is also constant for this case. Okay, for this case, so at will be constant. So since angular acceleration is constant, tangential acceleration will be constant. Okay, right. So now hereafter the problem is very simple. In fact, okay, it's very simple. See, constant in the sense, what does it mean? The alpha can be either plus something, positive, plus of something, or alpha can be minus of something. If alpha is positive, then omega will be keep on increasing, and tangential acceleration will be keep on increasing. And if alpha is negative, constant and negative, then omega will be keep on decreasing. So tangential velocity will be keep on decreasing. That we already discussed. That is what alpha signifies, right? Alpha positive means omega increases, which means Vt increases. Alpha negative means omega decreases, which means Vt decreases. And here alpha is constant, so it can be positive, it can be negative. If it is positive, it is acceleration. Okay, if it is negative, it is deceleration. Okay, angular deceleration, of course. Now coming to this case, like there for linear case, when linear acceleration is constant, by using these two equations, we got these, right? Now similarly, okay, similarly for linear and for angular, let us do one small comparison. Okay, in linear, what are the things we have? We have initial velocity, we have final velocity, we have acceleration, we have displacement, and we have time. Am I right? In case of angular, instead of linear velocity, instead of initial linear velocity, let me take initial angular velocity, which is omega naught. Final linear velocity, instead of final linear velocity, final angular velocity, let it be omega. Here acceleration, linear acceleration, which is constant, right? In case of angular case, it is angular acceleration, which is constant. And in case of linear case, yes, that is S is nothing but the displacement, and in case of angular, it is theta, which is nothing but angular displacement. And time will still remain as time only. Okay. Now, by using these two equations and by assuming acceleration to be constant, we got these three equations. Similarly, for angular acceleration, we have two equations. I hope that you remember. What is that? Omega is equal to d theta by dt. Okay, general equation. Okay, and similarly, alpha is equal to d omega by dt or d square theta by dt square. And by using these two equations and by including a condition alpha is equal to constant, okay, by including a condition alpha is equal to constant, listen carefully, linear equation, I introduced a condition acceleration constant, linear acceleration constant, I got these three equations, okay. Similarly, this is angular equation, angular velocity and angular acceleration. By introducing angular acceleration to be constant, I'm going to get similar type of equation but with these notations. So what I will be getting? Similar final there, so here also final, initial there, so here also initial angular velocity, okay, plus a, that is acceleration, here alpha, t, here t, okay. right? That is the first equation. Second equation, linear displacement, here angular displacement. Initial velocity, here initial angular velocity. Time only, plus 1 by 2. A, here alpha, here t, here also t. Okay. And last but not the least, final omega square, initial omega naught square plus 2 times of acceleration, here alpha, yes, here theta. Okay. So this is the three equation which we are getting under the assumption angular acceleration being constant. If angular acceleration is constant, tangential acceleration is also constant. So one more special case in circular motion. This is uniform circular motion. We already discussed about, we already know what is actually mean by uniform linear motion or simply uniform motion. If the body is moving in a straight line, okay, if the body is moving in a straight line, and if it moves with a constant velocity, okay, if it is moving with a constant velocity, obviously its acceleration will be 0, because acceleration is rate of change of velocity. So as acceleration is moving, acceleration is becoming 0, that particular body is said to be under uniform motion, okay, and it is linear motion because we are considering only the straight line motion, okay. Now coming to this case, circular motion, we already know that the particle is going to rotate, right? In case of circular motion, particle, this is origin, a particle is going to rotate, right? It's going to rotate, and when it is rotating, okay, when it is rotating with constant, it's rotating with constant angular velocity. If the particle rotates, that is, if the particle moves in a if the particle undergoes circular motion with a constant angular velocity, then I will be calling it as uniform circular motion. So obviously angular velocity is constant, so corresponding angular acceleration will be 0, because angular acceleration is rate of change of angular velocity. So angular velocity is constant, so angular acceleration was 0. Now we already know, if it is circular motion, these are something which is true, okay, these are something what I could say, which is always true, right? That is, r will be c, r dot will be 0, r double dot will be 0, radial velocity will be 0, tangential velocity is r omega, radial velocity is minus r omega, radial acceleration, I'm sorry, and tangential acceleration is r alpha. Now specifically for uniform circular motion case, alpha is 0, so this is 0, so tangential acceleration is 0, okay. Now if I draw that, okay, under uniform acceleration condition, okay, right, one thing is there is no radial velocity, only tangential velocity is there, so tangential velocity will be in this direction, vt is equal to r omega without no issues. There is no tangential acceleration is 0 because of alpha being 0, that is because of omega being constant, tangential acceleration is 0, but radial acceleration is there, which is minus r omega square. Minus indicates it should be pointing towards the center, so this is ar, which is minus r omega square. Here comes something which what I could say, most of you would have been wondering, if velocity is constant, acceleration has to become 0, right? Because in that case velocity is constant, so acceleration is 0. But in this case also angular velocity is constant, but only one component, see, angular velocity is constant, so this tangential velocity will also be constant, obviously, right? R is constant, omega is constant, so r into omega will be constant, no issues at all, okay, it has to be constant. Now then tangential velocity is constant, angular velocity omega is constant, Vr is 0, but still how does this radial acceleration term exist? That is something which you might have been wondering. I will give you the reason, a simple reason. Velocity is a vector, right? Velocity is a vector. So when can I call a vector to be not varying? When if it doesn't change in both its magnitude and direction. If any one changes also, then it is varying only. That case, consider that case, velocity. It's happily moving straightly only without any change in the direction, so velocity is constant, and there is no change in the magnitude also, so it's constant by its both magnitude and direction, okay, so acceleration was 0. But consider a particle. Consider a particle. Okay, consider a particle. Here, if it tries to rotate, okay, that is if it tries to undergo circular motion with some tangential acceleration. Of course, tangential acceleration magnitude will be constant, r into omega, it's going to be constant, no issues at all. But why this particular particle is rotating? Okay, why it is rotating? Why it needs to rotate? That is something which we need to understand. Just imagine, I'm taking this pen, I'm applying a tangential velocity. If I apply a velocity, it has to move straight, right? Obviously, if there is a particle, and if I apply a tangential velocity, it has to move straight only. It will try to move in this direction only. But it's non-intuitive. Like this particle is rotating. It is moving in a circular fashion. How does it move? I take an example of marker. I applied a tangential velocity. It has to move straight only. But just we will take a small. We will do one small change. Okay. I'm just connecting that marker to a thread. Okay, and I'm holding it here. Okay, I'm holding it here. Now apply tangential velocity. Now apply tangential velocity. What is happening? If I give some more velocity, then you will be able to see that. You could see, right, approximately. Okay, if I give some more velocity, you could see. Okay, so what is actually happening? If I give some more velocity, right? So what is actually happening? The particle is not moving in a straight line. Okay, if I keep a thread here, if I tie something here, and if I keep a thread here, and if I hold it, and if I apply tangential velocity, it will rotate. And why it is rotating? Why it is rotating? Why it is rotating? I am holding it here and it is rotating. The rotation is happening because there is some acceleration this particular thread is offering, and that is it is like pulling that. It is like pulling that towards. Okay, this thread is pulling this particular marker towards it. As it is pulling towards it, but this marker is trying to move straight, it's continuously changing its direction. Okay, it's happening something like this. When the particle was here, this is pulling it. Okay, this acceleration, okay, the radial acceleration is going to be responsible for this particle to rotate. Okay, the radial acceleration, which is just pulling this inside. Okay, pulling or pushing, I'm not sure, something. Okay, it is pulling it inside, and this tangential, because of that that effect, okay, that acceleration, instead of this particle moving in a straight way, it is rotating. Okay, I've given you a practical example also. If I'm holding it here and if I apply, there will be some acceleration which is going to pull. Okay, because of that, because of that, it is moving in a circular fashion. But if I'm not holding it and if I just apply, okay, if I just apply velocity, it will just move in a straight line, right? So even though velocity is being constant, still acceleration exists, and that acceleration is responsible for circular motion. Without that acceleration, circular motion cannot happen. Just imagine, I'm not tying the thread. Okay, I'm not tying the thread. I'm just applying it. It will happily move in a straight line only. But if I tie a thread and if I hold it and if I apply, it is going to rotate. Why? Because this thread is pulling it. Okay, so that pull, that acceleration, AR, which is equal to minus R omega square, is nothing but centripetal acceleration. Okay, it's nothing but centripetal. What is the conclusion which we can give? This acceleration AR, which that acceleration is something which is responsible for this circular motion. And how it is doing? See, this acceleration is pulling this particle towards, right? So this particle will move. Instead of moving it in a straight line, it will try to move it in a straight line only, but instead of moving it in a straight line, it will move in a circular path. Let us consider it is reaching here. Okay, it is reaching here. Now what will happen? My tangential velocity, it will be something like this, right? This is my tangential velocity, which is r omega. So what happened? Initially tangential velocity was facing this direction, now it was in this direction. So continuously this acceleration AR, okay, this acceleration AR, it's changing the position or changing the direction of tangential velocity. If there is no, listen carefully, if there is no AR, if there is no centripetal acceleration, what will happen? This particle will happily travel in a straight line in a linear fashion. And if a circular motion has to exist, then there has to be centripetal acceleration that will try to rotate the particle in a circular motion. Okay, so that's it. I hope that you would have understood at least somewhat regarding this centripetal acceleration, what is the meaning of it and all those things. Okay, so the things are, centripetal acceleration is something which is responsible for circular motion. If centripetal acceleration is something which is causing the change in the direction of Vt, and because of that change in the direction of Vt only, circular motion is happening. And if centripetal acceleration becomes zero, that is if r omega square becomes zero, then there is no circular motion, it will be a straight line motion. Okay, so that's it. So for a circular motion, even though omega is constant, angular velocity is constant, there will be an acceleration component, but that is not true for uniform motion, that is linear motion. A will be zero if V is constant. Okay. Let us start discussing the problems from circular motion. Okay, so the first question: when particle moves in a circle with uniform speed, okay, when particle is moving in a circle with a uniform speed, they are asking about the conclusion, right? So before entering into this, let us first recollect the things. If any particle moves in any circular motion, not necessary that acceleration has to be constant, not necessary that uniform speed, any circular motion, what are the conditions which we have? This is very simple condition. Radius will be constant, so obviously r dot, the first derivative will be 0, second derivative is also going to be 0. Since first derivative is 0, radial velocity has become 0 because radial velocity is r dot, which has become 0. So we will have only tangential velocity. If it is in the case of circular motion, there is no radial velocity. Now coming to acceleration, as r double dot is 0, in radial acceleration r double dot will become 0, and similarly we know that radial velocity was 0, so 2vr omega, that is the Coriolis's component, that also will become 0. So radial velocity I will have only minus r omega square, tangential velocity I will be having only r alpha. This minus r omega square has a special name, which is centripetal acceleration. We already know that the centripetal acceleration is something which is responsible for the particle to rotate in a circular motion. Okay, and r alpha, that is tangential acceleration, is responsible for changes in tangential velocity or omega, that is angular velocity. If alpha is positive, omega will be increasing. If alpha is negative, omega will be decreasing, as we already discussed it. Now coming to this case, uniform speed case. What does it mean? Omega is constant. Okay, so omega constant means alpha will become 0. Accepted. That is, we clearly know that, right? So omega constant, so Vt is also constant. So velocity will be velocity, that is tangential velocity, will be constant. Okay, now let me just fix this. Tangential velocity will be constant. Let me just fix this. Now coming to acceleration, so now coming to acceleration, we have, let me draw the diagram. So if this is the circular path, so this is going to be my tangential velocity Vt, right? And it is rotating with a constant angular velocity omega. Okay. Now regarding the acceleration, we know that omega is constant. So let me come back. Let me come to this case. Alpha has become 0. Okay, since alpha becomes 0, at will be 0. Okay, there is no tangential acceleration, but omega ar will be there, right? Ar is going to be minus r omega square. Okay, so ar is equal to minus r omega square. Now listen carefully. Listen carefully. The general answer which you are going to give now, okay, the general answer which you are going to give now will be option A. Why? Because it's pretty obvious. Omega is constant, so r into omega, so Vt is constant. Okay, and similarly r into omega square, so ar, that is acceleration, is also constant. That is something which you will be thinking. So the correct answer might be option A, right? The correct answer might be option A, but that is wrong. Option A is not correct answer. The correct answer is, I will be giving you, just wait for a moment. See, tangential velocity is not changing, accepted, but only magnitude is not changing. here tangential velocity is acting in this direction, but if as it is keep on rotating, here the particle will reach this place. Now here tangential velocity will be acting like this, here tangential velocity will be acting like this, here tangential velocity will be acting like this. So direction continuously changes, direction continuously changes. Okay, so which implies tangential velocity is not constant, it is changing. Magnitude is constant, but direction is continuously changing. Similarly, acceleration also. Now acceleration is acting like this, right? For this particle, acceleration will act like this. For this particle, acceleration will act like this. Of course, the acceleration is acting towards the point only. That is accepted. Acceleration is acting towards the center only. But as the particle keep on rotating, from here, if the particle reaches here, the direction of acceleration is changing. Now from here, particle reaches here, the direction of acceleration is changing. So in the rotational motion, as the particle keeps on, that is in a circular motion, as the particle keeps on rotating, the direction of acceleration is also changing. The direction of radial acceleration, centripetal acceleration. So that is changing. So direction of both tangential velocity and radial acceleration is changing. So correct answer for this question was option D. Okay, it is not option A. Okay, it is not option A. So when a body undergoes circular motion in uniform speed, its both velocity and acceleration will change. Okay, accepted. What is that? Tangential acceleration is becoming zero, and then radial velocity is anyways already zero. Similarly, tangential velocities magnitude. Okay, tangential velocities magnitude will be constant. Similarly, magnitude of centripetal acceleration is also constant. But as you could see, if I take a particle here, my tangential velocity was this, and my acceleration was this. But if I take a particle here, this is going to be my tangential velocity, so it is acting in this direction, and this is going to be my what is that acceleration. So acceleration direction and velocity direction is continuously changing. So option D is correct. So next question, a stone of mass m tied to a string. Okay, let us consider this is the stone. Okay, and let us consider this is the string. Okay, this is the string. Okay, so a stone of mass m, it is tied to a string. Okay, of length L, is rotated in a circle. So as you could see, they given that it is rotating in a circle. So let me just take that it is rotating in circle, something like this. Okay. So it is rotating in a circle with the other end of the string as a center. Yeah, that we know. This is the center and this is the string. Okay. Now the speed of the stone is v. Okay, so if it is moving, if it is a rotating motion, then we obviously know that there is going to be only one velocity, which is tangential velocity vt. Okay, so that is given as v. Now if the string breaks, very good, listen, if the string breaks, the stone will move towards the center, away from the center, along a tangent, will stop. Obviously everyone knows it will not stop. And like mostly if you think intuitively, you will understand that there is no possibility for it moving towards the center, also. You would have experienced that. But anyways, let us try to prove it. Listen carefully. A particle is there. If I'm applying some velocity v, it will happily move in a straight line only. But why this ball or this stone is rotating? It is because of this string. Okay, it is because of this string, and this string, it is because of the string, and the string is causing, or the string is producing the radial acceleration. Okay, we already know, right? Centripetal acceleration minus r omega square, and this radial acceleration is pulling, right? If there is a string, that string will pull this. The string will pull this stone towards the center. As it is pulling towards the center, the stone cannot move straight. Happily, it cannot move straight, so it is starting to change its direction. Okay, it's starting to change the direction. It's starting to change the direction. Why it is happening? Because this string is pulling the mass towards it. It's trying to pull the mass towards it by applying an acceleration AR, and obviously AR, that is radial acceleration or centripetal acceleration, is responsible for this particular stone to move in a circular motion. So now I am cutting this off. I'm not cutting it, it's breaking. Okay, the string is breaking. So if the string breaks, what will happen to the mass? Obviously, the mass will travel straight without any issues. It will travel straight. Okay, so that is what straight means. In this case, it is tangential, right? Tangential to the circle, okay, along a tangent. So it will move along a tangent. So correct answer is option C. It's not going to move along a center. It's not moving away from the center also. It is not going to stop also. If the string breaks, it will move straight without any issues. Why initially it is not moving straight? Because of the string, there will be an acceleration, and that acceleration is pulling towards the center. So only this mass is moving in a circular manner. Okay. So let us continue next question from circular motion. A merry-go-round rotates from rest. Okay, a merry-go-round rotates from a rest. So they given that it is at rest. See, we are dealing with circular motion. So since it is at rest, we will take anyways. Velocity is also linear velocity is also zero, and similarly angular velocity, initial angular velocity is zero because they given that it is at rest, right? With an angular acceleration of 1.5 radian per second. So okay, so angular acceleration is given as 1.5 radiation per second square. How long does it take to rotate through first two revolutions? Okay, first two revolution, which means theta was 2 revolution. What does it mean by 2 revolution? See, if I take a particle, in this case it is merry-go-round, right? So the merry-go-round, if suppose a child is there, he's sitting here. Okay. So one complete revolution means when it completes this one full circle. Okay, one complete revolution or one revolution. So two revolution in the sense when it completes two times of the circle. So for completing one time this circle, it require 2 pi angle, right? This particle has to travel 2 pi distance. Now for two revolution, it's going to be 2 into 2 pi, which is nothing but 4 pi. Okay, so the theta value will be 4 pi. So total angular displacement was 4 pi. So now they are asking how long does it take? Okay, how long does it take for completing this two revolution? So how to solve this? Simple, we know omega naught. Alpha is given 1.5 radian per second. It is constant, right? It is constant. It is not varying with anything. And they also said that theta, okay, angular displacement is also given. So I can use our second equation for constant angular acceleration. What is that second equation? Theta is equal to omega naught t plus 1 by 2 alpha t square. Already we know omega naught is 0, so this is 0. Theta is 4 pi. 1 by 2 alpha is 1.5 into t time taken, that is something which I need to find out, so which will be equal to t square is equal to 8 pi. I will divide it with 1.5. Now take square root on both sides. After dividing this, take square root on both sides. You'll be getting time, so that is going to be equal to 4.1 seconds. Okay, so correct answer here was 4.1 second, which is option D. So let us continue the next question. The wheel of motor is accelerated uniformly from rest. See, two words to highlight here. One is they given it is accelerated. It is accelerated uniformly. Okay, accelerated uniformly, and the second word to note was from rest. What does it mean? There is a wheel and the wheel is rotating and it is accelerated uniformly means under uniform acceleration, or in another word, constant acceleration. So angular acceleration was constant. And they given that it is at rest. Since it is rotating, we are going to consider omega, that is angular velocity. So omega naught is going to be 0. Okay, it is at rest. So omega naught is 0. It rotates through 2.5 radian during first second. That is, during when time was 1 second, the angular rotation was 2.5 radians. Okay, so yeah. Now they are asking what is the angle which is rotated during the next second. Okay, so during the first second, the rotation was 2.5 radians. Okay, and now during second, what is going to be the rotation? That's what they're asking. Right, so let us try to find out what are all the unknowns which is available. See, first we have alpha. We don't have alpha. Okay, alpha they given it as constant, but we don't have alpha. But we know initial velocity, we know time taken, initial velocity is 0 anyways, initial angular velocity, and we know angular displacement. So by using these three equations, I can easily find out alpha. How can I find out? Simple, we know the basic equation, right? It is a constant acceleration, so theta is equal to omega naught t plus 1 by 2 alpha t square. Already omega naught is 0, so that will become 0. So theta is 2.5 radian, okay, 2.5 radian, which is equal to 1 by 2 into what is alpha? Alpha is not known, so alpha multiplied by time taken, which is once again, so 1 square. So alpha is going to be, just bring this to that side, so it becomes 5, okay, so alpha is going to be 5 radian per second square. So we got alpha. Now with this alpha, what I can do? See, this is theta 1. Okay, what is mean by theta 1? During 1 second, this is how it is rotating. Okay, let me take circular motion. So there is a particle. Okay, during first 1 second. Okay, during first 1 second, a small rotation has happened. Okay, a small rotation has happened. That is 2.5. Okay, during second, during the second, we will use another color. This much rotation has happened. Okay, this much rotation has happened. Okay, so this is theta 1. Okay, this is theta 1, and theta 2 will be this much, right? Theta 2 will be this much, which means from the starting, from time is equal to 0 until time reaches 2 seconds, this much deformation or this much angular displacement has happened. So that is going to be theta 2. So theta 2 is the angular displacement from the beginning. Okay, from the beginning. But what actually they are asking? They are asking us to find out angle rotated during next second. Listen carefully. Let us consider this is how it has traveled during first second, and during the second, this is how, okay, it has rotated. So overall, if you observe, okay, overall if you observe, during first once again, this is the angle it has rotated. And then during second once again, this is the angle. Okay, this is the angle. I will highlight it with another color. This is the angle it has rotated. Okay, this is the angle it has rotated. But theta 2 indicates what? Theta 2 indicates for complete 2 seconds. Okay, for complete 2 seconds, which means from the beginning. Okay, from the beginning until the ending, what is the angular displacement? Which means this total angle is represented by theta 2. Now if I want to find out, this angle, that will be simply delta theta is equal to theta 2 minus theta 1. Okay, so theta 1 is indicating during 1 second, how much angle it has been turned, angular displacement. Theta 2 indicates for 2 seconds. Okay, from the beginning, that is also important, from the beginning until ending of 2 seconds. So for 2 seconds, um, how much angular displacement that particular motor, okay, wheel, okay, has traveled. So theta 2 will be equal to, again, okay, so when time was 2 second, okay, when time was 2 second, by using this formula I can find out theta 2. Okay, theta 2 is equal to omega naught into t plus 1 by 2 theta t square. So, I'm very sorry, alpha t square. Okay, alpha t square. So alpha t square. See, anyways, initial velocity at the beginning, okay, at the beginning, omega naught was 0, right? So this has become 0. Now we determined alpha, okay, from this equation. And what is theta 2? That is, I don't know. Okay, theta 2 will be equal to 1 by 2 into alpha is 5. Time taken was 2 seconds. Okay, so for 2 seconds, this is the angular displacement that wheel has traveled. Okay, so I can cancel this, so it becomes 10 radian per second. So theta 1 is 5 and theta 2 is 10. So what is going to be our delta t? What is delta t? During second, okay, during second, how much angular displacement has happened? That is nothing but theta 2 minus theta 1. So 10 minus 5, which is going to be 5 radian per second. Okay, so 5 radian per second, right? This is theta 2 is 10. I'm sorry, theta 2 is 10. Theta 1 is 2.5. So 10 minus 2.5, it is 7.5. I'm very sorry for that. It is 7.5. Okay, it is 7.5. Okay, so theta 1 is nothing but during 1 second how much angle it has turned. theta 2 is nothing but during 2 seconds how much it has turned. Delta theta is nothing but during the second. Okay, so first second will be there. First during the second. Okay, during the second how much angle has been turned. Okay, that can be given by theta 2 minus theta 1, which is nothing but 10 minus 2.5, which is 7.5. So correct answer here is, very sorry, it is not radian per second because it is angle, right? Angle means just radian only. Let me erase this also. This is not radian per second, just radian. Okay, so theta 2 it is 10 and theta 1 it is 2.5. So 10 minus 2.5, that is going to be 7.5 radian. Okay, next question here, the magnitude of linear acceleration. Okay, they are asking what? Linear acceleration of a particle moving in a circle. Okay, so let us consider there is a circle, something like this. The particle is moving in a circle. Okay, the particle is moving in a circle, and they are asking us to find out the magnitude of linear acceleration. See, first of all, first and foremost point, if there was a circular motion, okay, if there was a circular motion, totally how many acceleration will be there? Two acceleration, right? That's going to be radial acceleration, or in general, two acceleration will be there. Whatever, if it undergoes some general motion, radial acceleration and tangential acceleration in case of Cartesian coordinate system. If it is undergoing circular, then r will be constant, right? R will be constant. So r dot is 0, r double dot is 0. So which means radial acceleration has become, one radial acceleration has become 0. So only one radial acceleration will be left out. That is going to be minus r omega square, which is centripetal acceleration. And talking about tangential acceleration, one will be Coriolis's component, another will be r alpha. But anyways, Coriolis's component will be 0 for a circular motion. So there is going to be only r alpha. So two acceleration are there, radial one, tangential one. Okay. Now let us proceed with the question. So circle of a radius is 10 centimeters. So the given radius is 10 centimeter, which is 10 into 10 to the power of minus 2, which is 10 power minus 1 meter. Okay. With a uniform speed, keyword here. Okay, uniform speed. What does it mean by uniform speed? Here we are dealing with circular motion. So here omega, angular velocity or angular speed, is constant. It is completing the circle in 4 seconds. So it is completing the circle, which means what? A particle is starting here. It is rotating over a circle. It is rotating over a circle, and again it is coming back here. So what is going to be my angular displacement? It is simply 2 pi. Okay, simply 2 pi, 360 degree. Okay, 2 pi. So angular displacement was 2 pi. So now ultimately we have omega. We don't know omega, but we know omega is constant. We have time, we have theta. Okay, and by using omega constant, what I can conclude, very important conclusion, since omega is constant, we know alpha is nothing but what? D omega by dt, right? So d omega by dt, so differentiating omega with respect to time, it becomes 0. So alpha is 0. Since alpha has become 0, r alpha is also 0. So our acceleration, in general, if I want to write, acceleration will be a radial acceleration square plus tangential acceleration square. But in this particular problem, as tangential has become 0, so tangential will be 0. So our acceleration will be root of ar square, which is going to be ar, which is going to be equal to minus r omega square. Okay. Right. So how can I find? I know theta, I know t. I can use that formula. Theta is equal to omega naught t plus 1 by 2 alpha t square. And already we know alpha has become 0 because it is moving with uniform speed, which means omega is constant. So omega is constant, so omega naught or omega both are same, which is equal to omega into time taken is 4 seconds for completing a rotation of 2 pi. So omega will be equal to 2 pi by 4, which is equal to pi by 2 radian per second. So this is omega. What will be my acceleration finally? My acceleration is going to be minus, radius is given 10 power minus 1, that is 10 centimeter, which is 10 power minus 1 meter. So 10 power minus 1 into pi by 2 acceleration. So it is, I'm sorry, linear acceleration, don't forget that. So it is meter per second square. So once if you solve this, you will be getting the final one. I'm sorry, I did one mistake here. This is going to be pi by 2 whole square, right? Because omega square, so pi by 2 whole square. So once if you solve this, I will just keep this pi square separately. Okay, so if I solve this, I will be getting a point. Um, just a moment. So let me erase this. Okay, so that I will have a space. Yeah, so I can just concentrate on writing it here. I'm very sorry for that. Yeah, so now if I solve this, listen carefully. One point I didn't see properly when I was solving here. They asking us to find out in centimeter per second square. So what I will do, I will substitute it in centimeter itself instead of substituting it in meter. I will substitute it in centimeter itself. So if I do that, minus r value. So they are asking only magnitude. So let me just keep it as plus. They're asking only magnitude, so no issues, just plus. Radius is 10 centimeter into omega is pi by 2, which we already determined, so pi by 2 square. So 2 square will be 4, so 10 by 4 is going to be 2.5. Okay, 2.5 pi square radian per, and again I'm very sorry, meter per second square, because this is linear acceleration. Okay, meter per second square. Okay, so why I'm making minus s plus, because they are asking only magnitude. Okay, they are asking only magnitude. So 2.5 pi square, which is option C. Right, let us start the next question. They given that a particle travels in a circle of a radius 20 centimeter. So they given radius of the circle as 20 centimeter, which is nothing but 0.2 meters at a speed that uniformly increases. So speed is increasing uniformly, which means it is accelerating. Okay, it is accelerating. Okay, which is accelerating. Now, if the speed changes from 5 meter per second to 6 meter per second, see they given speed. Okay, so initial speed was 5 meter per second. It is changing to a final speed of 6 meter per second. And what is the time taken? The time taken was 2 seconds. Now the question is, the angular acceleration is dash, which means alpha. Okay, now how to find out? See, we can use the equation. Okay, constant acceleration equation. The fact here is they didn't given anything like what is that? They didn't given anything related to omega. Okay, they didn't talk anything related to omega. One more point to note here. They said that speed increases uniformly. Okay, when speed will increase uniformly? Speed will increase uniformly only if acceleration is constant. Okay, what does it mean by uniform increase in speed? For example, in this case, they given from 5 meter per second, it is increased to 6 meter per second in 2 seconds, right? Now, for the next another 2 seconds, there will be further increase of 1 meter per second. Okay, that is what, like uniformly it is increasing. Okay, with respect to time, the change in speed is not changing. Okay, so with respect to time, the rate of change of speed is not changing. What does it mean? Acceleration is not changing, which clearly indicates that acceleration is constant. Okay, acceleration constant means here we are dealing with circular motion, so alpha is constant. I will just mark it down as alpha. Okay, now alpha is constant. I need to find out that alpha, so I can use simple equation. This equation, omega is equal to omega naught plus alpha t. I can use this equation because alpha is constant, but the issue is I don't know omega, I don't know omega naught. But instead of that, they given u, they given v. So from u, I need to find out omega naught, and from v, I need to find out omega. How can I find out? Again, simple. It is circular motion. A particle is undergoing a circular motion. Then only one velocity will be tangential velocity, no other velocity, which you already know. Radial velocity will become 0. So only one possible velocity, which is tangential velocity, which is r omega. Okay, so u will be equal to r into omega. Radius is constant anyways, so r into omega naught. Similarly, v is equal to r into omega, that is the final velocity. Okay, which is equal to r is how much? 0.2 meters into omega naught is not known. U is given as 5, so which implies 5 by 0.2, which is nothing but 25, right? So omega naught is equal to 25 radian per second. Now what about v? V is given as 6 meter per second. R is again 0.2 into 0.2 multiplied by omega, which implies omega is equal to 6 by 0.2, which is 30 radian per second. Okay, so omega naught is given, omega is given, substituted here. So 30, which will be equal to 25 plus alpha is not known. Time taken is given as 2 seconds. Okay, so subtract this there, so it will become 5. So alpha is equal to 5 by 2, which is nothing but 2.5. 2.5 radian per second square. Let me write it here separately. Alpha is equal to 2.5 radian per second square. Okay, so the correct answer is option C. So next question, a particle moves in a circle of radius 20 centimeter. So radius of the circle is given as 20 centimeter, and if its linear speed is given by, okay, they given linear speed, okay, v. Okay, so linear speed is given by 2 times of t. Okay, in terms of time they're given, where v is in meter per second, t is in second. Okay, find the radial acceleration of the particle at t is equal to 1 second. So when time becomes 1 second, I need to find out. First question is they are asking radial acceleration, which is AR. The second question is they are asking tangential acceleration AT. The third question is magnitude. First of all, radial acceleration. It is moving in a circle, right? So radial acceleration is going to be minus r omega square. If it is only magnitude, you can just remove the minus sign. Okay. Tangential acceleration, it is going to be Coriolis's component is 0, so only acceleration will be r alpha. And normal acceleration is going to be root of, that is magnitude will be ar square plus at square, as we know already. Now what is ar, what is at? That is what we need to find out. So for finding that, we need omega when time was 1 second. Okay, that is something which is important. Omega when time is 1 second. Similarly, alpha when time is 1 second. So how to find that? For that only they given v is equal to 2t, right? They given a clue. So what I can do, v is equal to 2t, which is nothing but r into omega. Am I right? So at t is equal to 1 second, and we already know radius is 20 centimeter, which is nothing but 0.2 meters. Okay, so now substituting there, 2 into 1, which is equal to 0.2 into omega. So omega will be 2 by 0.2, which is going to be 2 and 2 will get cancelled, so which is 10. Okay, so 10 radian per second. This is omega at what point? When time is how much? When time is 1 second. Okay, when time is 1 second, omega was 10 radian per second. So now directly by substituting this, I will use another color. Okay, by substituting this, radial acceleration when time is 1 second. Okay, radial acceleration when time is 1 second will be equal to minus r is 0.2 into omega was 10, right? So 10 square, which is equal to minus 0.2 into 100, which is simply 20. Okay, minus 20. Unit will be in terms of meter per second. Okay, so sorry, meter per second square acceleration. Radial acceleration when time is 1 second. So we identified radial acceleration. Now, how to find out tangential acceleration? For tangential acceleration, I need alpha when time is 1 second. So how to solve that? Simple, we know velocity is equal to 2 times of t, right? And that is nothing but r into omega. Differentiate this on both sides. Okay, that is differentiate this equation on both sides. If I differentiate it, 2 will be constant. Differentiate with respect to time. Okay, differentiate with respect to time. So if I do that, t will become 1 anyways. Okay, differentiation of time with respect to time will be 1. R into omega, r is anyways constant, so I'm bringing r this side, and differentiation of omega with respect to time. And what is this d? What is this d omega by dt? That is alpha, right? D omega by dt is alpha, and left hand side I have 2. And this is nothing but what? R alpha is nothing but a tangential. So I got a tangential to be 2. Okay, so a tangential to be 2. Okay, 2 meter per second square. I'm just converting this by differentiating it so that I will be getting tangential acceleration. So now I got radial acceleration, I got tangential acceleration. So what we are left out with? Magnitude. So that is going to be equal to, okay, that is going to be equal to root of radial acceleration is 20 meter per second, 20 meter per second square, plus tangential is 2 meter per second square. So solve this. So that is going to be root of 24, right? Root of 24, which will be equal to 20.09. So the final answer, okay, radial acceleration was minus 20 meter per second square. Tangential acceleration was 2 meter per second square, and finally magnitude of the acceleration was 20.09 meter per second square. Okay, next question. A particle of unit mass. Okay, sorry, a particle of unit mass is moving on a plane. Okay, so it's a planar motion. A particle is undergoing a planar motion. Its trajectory in polar coordinates. Listen carefully. It is not a circular motion. Why? Because they given some other trajectory, right? What does it mean? If suppose a particle is moving like this, okay, a particle is moving like this, r comma theta, okay, it is mentioned as t square comma t. Okay, they are not mentioning it as circle, because for circle we already know the general form, right? We already know the general form. This is r will be like, yeah, so this is going to be r comma theta, and we know that r is nothing but let me erase it and write it properly, I'm sorry. This is in fact theta. Okay, I just missed that. This is in fact theta. So if a particle moves in a circular motion, we know that r will be equal to root of x square plus y square. X square is nothing but this distance, and y square is nothing but this distance. So r can be determined, that is hypotenuse square will be equal to adjacent square plus opposite square, right, by using that formula. And theta will be equal to tan inverse of y by x. And this is something which is different. They given r and theta in terms of time, okay, in terms of time. Also based on the time, r and theta is going to vary. So r is not constant in this case, but for a circular motion r will be always constant, as we know already. So this is not a circular motion. This particle is not undergoing a circular motion, right? So a general motion, but they are mentioning it in terms of polar coordinates. Now how to solve this? They are asking velocity of the particle. See, if I take any particle which is undergoing any motion, broadly it will have two types of what is that, two types of acceleration, sorry, velocity. One is radial velocity, okay, one will be radial velocity, okay, and another one will be tangential velocity. For circular motion, radial velocity will become zero, because radial velocity is nothing but r dot. Since r is constant, radial velocity has become zero for circular motion. But this is a general motion, so r dot will be there. What is r dot here? Just differentiate this t square. T square is r, right? T square is r. So differentiate this t square, which is nothing but 2t. Okay, so vt is nothing but r into omega. Okay, so which is equal to r is what? T square. And what is omega? Omega is nothing but dt by dt, sorry, d theta by dt. Theta is given as t. Okay, theta is given as t. So differentiation of theta with respect to time, it becomes 1. Okay, so this is going to be 1. So now I got Vr, that is radial velocity, which is 2t, which will be, okay, they are asking at what time, that is also important, right? They are asking at time t is equal to 2 seconds. So Vr when time t is equal to 2 seconds, okay, that will be equal to 2 into 2. Okay, simply I'm substituting in place of time, I'm substituting 2, so that is 4 meter per second. Okay, 4 meter per second. And what will be my tangential velocity? Tangential velocity is t square into 1, right? So t square time, that is given as 2 seconds, right? For us, let me write it in another color. Time, that is 2 seconds. So in place of t, I'm substituting 2, so 2 square into 1, which is again 4 meter per second. So both radial acceleration, tangential acceleration is 4 meter per second. So what will be my final answer? That is the total acceleration. That's going to be root of vt square plus r square. That is nothing but root of 4 square plus 4 square. 2 times of 4 square, so 4 I can take it out. So 4 into root 2. Okay, so which is option A. So let us proceed to the next question. A rigid link PQ. Okay, so there is some rigid link. Let us consider that this is the rigid link, okay, PQ, and of length 2 meters. They given the length of this rigid link is 2 meters. Rotates about a pinned end Q. Okay, so let us consider here there is a pin. Okay, there is a pin joint at one end. Okay, so this is P and let this be Q with a constant angular acceleration. So they mentioned that it is rotating with constant angular acceleration. So alpha is 12 radian per. So it is rotating with 12 radian per second square angular acceleration, and they given that it is constant. When the angular velocity of the link is 4 radian per second, so they given that angular velocity omega as 4 radian per second. Okay, they are asking what is the resultant acceleration at the end P. Okay, so at this end, what is the resultant acceleration? That's what we need to find out. So this particle point P, okay, the particle at this point P, what type of motion it is going to undergo? What type of motion it's going to undergo? Just think. Very simple. This particle P is going to undergo a rotatory motion or a circular motion about this point Q. Okay, so if a particle is undergoing circular motion, what are all the different types of acceleration it's going to have? It's going to have one acceleration, radial acceleration, which is nothing but centripetal acceleration minus r omega square. And another acceleration is going to be tangential acceleration. See, as it is rotating in this direction, okay, as it is rotating in this direction, alpha is also in that direction. So tangential acceleration will also be in the same direction. I'm sorry. Tangential acceleration will also be in the same direction. Okay, so this is going to be tangential acceleration, and that's going to be equal to r alpha. Okay, so this is tangential acceleration, this is radial acceleration, and the resultant, okay, the resultant is going to be something like this. Okay, so this is the resultant acceleration. That resultant acceleration will be equal to root of acceleration tangential acceleration square plus radial acceleration square. So the resultant acceleration will be equal to, we can find them individually. Okay, so first I will find out radial acceleration, which is minus r omega square. So minus, what about radius? Radius is radial distance, right? So from this point, about the point where it is rotating. So Q is the point about which this link is rotating. P is the point where I need to find out the acceleration. So 2 meter is the distance between them. So 2 meter is the radius. Okay. Into omega, it is rotating with omega 4. Okay, so 2 into 16, which is 32 meter per second square. Okay, now coming to tangential acceleration, r alpha, right? R alpha. Again, radius is 2, alpha is given as 12, so 12 into 2, which is 24 meter per second square. Now substitute them both. Tangential acceleration is 24 meter per second square whole square plus radial acceleration is 32 minus 32. Anyway, square it will become 32. So 32 square. Okay. So square it, add it, and find square root. You will be ending up with 40. Okay. So 40 meter per second square. So that is the answer. The answer for this question is 40. So consider an ant crawling crawling along a curve x minus 2 whole square plus y square is equal to 4. So what type of curve is this? It is clearly a circle, right? It is clearly a circle. Let me just first plot down the, what is that, coordinate axis. This is our y-axis, this is our x-axis. And first of all, we need to find out the points, right? Yeah. X minus 2 whole square plus y square is equal to 4. So we know the general form, x minus x1 whole square plus y minus y1 the whole square, which is equal to radius square, where this x1 and y1 are nothing but center, and this r is nothing but the radius. So here x1 is 2, right? Here x1 you could see here x1 is 2 and y1 is anyway 0. So center is going to be 0 comma 2 and radius is going to be 2. So radius is 2, center is 2 comma 0. Okay, sorry, not 0 comma 2, 2 comma 0. So 2 comma 0 lies somewhere here. Okay, and radius is 2, right? So this side is 2, this side is 2, and similarly top 2, bottom 2. Okay, let me erase this. So if I go left side by 2, okay, if I go left side by 2, then it will be, this will be the point, right? 0 comma 0. And similarly, if I go right side by 2, this will be the point, which is going to be 4 comma 0. Okay, because center point is how much? Center point is 0 comma 2. So center point, very sorry, center point is 2 comma 0. So that is what we are getting like this. And similarly, what about the top point? What about the top point? Top point is going to be, like, again I need to shift by 2 units. Okay, so that is going to be 2 plus 2, so it's going to become 2 comma 2. And similarly, bottom I need to shift by 2 units, that's going to be 2, and it is going to be minus 2. Okay, so now this is how I will be getting my circle. So if I join this, I'm not getting exactly as a circle, but approximately you can just consider it to be circle. Okay, we will consider this is our point. Okay, that is 2 comma 2 comma minus 2. Okay, now coming to the question, an ant is crawling along the curve. So ant is crawling means it is just moving along this curve, and they given ant starts at a point 4 comma 0. So 4 comma 0, where it is, this is 4 comma 0. Okay, this is 4 comma 0. So ant is starting here, and it is moving in a counterclockwise direction. Counterclockwise means what? This direction, with a speed of 1.5 meter per second. What will be the speed? 1.5 meter per second. So ant is moving in a circular path. So obviously the tangential speed, okay, or tangential velocity, okay, velocity of ant, which is nothing but tangential velocity, which is equal to 1.57 meter per second. Okay, this is given. And now with the speed of 1.5 meter per second, okay, the time taken by the ant to reach the point 2 comma 2. So from here it is keep on scrolling along this curve. Okay, along this white color line it is scrolling, and it is reaching 2 comma 2. So the length or the distance it has traveled, I will show you in another color. From here it is moving. This is how. Okay, it started from here, and it is moving along the curve. Okay, this line has to be along the curve, and it reached here. Okay, this is the distance it has covered. Okay, now they are asking us to find out time taken. How can I do? Simply I can do this problem by using polar coordinates. You could see here, from this line, the ant has traveled until this point, right? So which means it has covered 90 degree, okay, which is pi by 2. Okay, so theta, the angular displacement was pi by 2. Okay, and we already know the radius. What is radius? Radius is 2. Now I need to simply find out what I need to find out. I need to find out the time taken. So how can I find out? Simple. See, ant is moving with an velocity 1.5 meter per second. It is not changing its velocity, which means acceleration was constant. They didn't say anything about the variation of acceleration, right? So angular acceleration is constant because we are dealing with circular motion. So angular acceleration is constant. So as alpha is constant, what I can do? I can simply use theta is equal to omega naught t plus 1 by 2 into alpha t square. And anyways, sorry, I'm very sorry. One small mistake I did. Acceleration is 0. Okay, acceleration is 0. I'm very sorry. They didn't say anything about acceleration, right? They didn't say that it is accelerating. They said that the ant is moving. Okay, ant is just moving with the speed 1.57 meter per second. Just ant is starting from this point, and it is moving with a speed of 1.57 meter per second. That's it. They didn't mention that it is accelerating. They didn't mention that the velocity is increasing. They didn't mention that velocity is decreasing. So obviously it is not accelerating or it is not decelerating. It is just traveling with the same velocity, 1.57 meter per second. So which means alpha will be 0. So this term will be 0. Now theta, how much? Pi by 2. Omega naught, or just omega, because omega naught will be equal to omega, right? Because since acceleration is 0, it is traveling with the same velocity only. Okay, omega into t. Now I need to find out this omega. How can I do? That is where they given tangential velocity. This ant is moving in a circular path, so obviously it will have only tangential velocity. Which is going to be equal to r into omega. So omega will be nothing but vt by r. So what is vt? 1.57 by radial distance, it is 2. Okay, so 1.57 by 2, which is going to be approximately 0.785. I hope so. Yeah, it is 0.785. So from this, t will be equal to pi by 2 into 1 by 0.785. I'm just bringing this gamma, this omega this side. So finally my time, okay, time taken will be equal to 2 seconds. You just cancel it and you solve it. You will be getting 2 seconds. So correct answer is 2 seconds.